Let us try to understand the estimation of power loss that occurs in switches in a power electronic converter with certain example. There is a source, DC source VD, and it is connected to a resistor through a switch. So the current flowing through the switch is IS and the voltage across the switch is Vs. The power loss that occurs in the switch can be calculated by looking at the product Vs multiplied by Is. Let us take a switching pattern for this particular switch. So let's say the switch is off to start with, and then it is turned on at a certain instant. But ideally the switch would have turned on instantaneously, but in reality it will take some time to turn on. So that is denoted by this off to on state, off arrow on, that is off to on state here. And then the switch is on for certain duration, and then we have initiated the turn off process of the switch. So that is the interval of turn off is indicated by on arrow off, and then the switch turns off and this cycle continues. Let us try to look at the voltage and current corresponding to the switch. That means the voltage across the switch and current flowing through the switch over this switching cycle. So when the switch is off, how do we get the voltage? We apply KVL. So KVL, if you apply in this loop, Vs is equal to Vd minus Is times R. So switch is off, so the current through the switch is 0. So Vs is equal to Vd. So that is what is shown here. Now when you initiate the turn on process at this instant, at this particular instant, what happens? The current through the switch starts rising. So since the current is rising, what happens to the voltage across the switch? Vs is equal to Vd minus Is times R. Is was earlier 0, now Is started rising. So this IR drop will start increasing. So that means the voltage across the switch will fall simultaneously. So that is what is shown here. The voltage across the switch, shown in green color waveform, falls during the turn on transition, and the current through the switch rises in the same interval. Now when you initiate the turn off transition, again the current starts falling and the voltage rises. Both occur simultaneously in this interval. And what happens in the on interval? Once the switch is on, ideally the voltage across the switch should be 0, but in reality there is a finite forward drop, voltage drop across the switch, and that voltage drop is denoted by V subscript on. Now if we look at the power waveform, which is a product of voltage and current waveform, it looks like this first purple color waveform shown here, PS, which is the product of Vs times Is. So we are multiplying two straight lines, so we should get something like a parabolic shape. So that is what is shown here. If you look at the intervals in one switching cycle, which is the duration of Ts, there are 4 intervals. T off interval, where the switch is completely off, and then there is an interval TSW on, that means the turn on transition interval, where the transition from off state to on state is happening, and then there is T on, the time interval for which the switch is completely on, and then the turn off transition interval, so that is denoted by TSW off here. So sum of all these 4 intervals, T off plus TSW on plus T on plus TSW off, is capital T with a subscript S, TS, which is known as the switching cycle time period, and the inverse of that is switching frequency, the frequency at which a particular switch is turning on and off in a power electronic circuit. It is worth to note that the current carried by the switch when it is on depends on the external circuit elements Vd and R in this case, and the voltage across the switch when it is on is often a function of the current flowing through the switch. That is what is shown here. V on is a function of I of S. And the voltage blocked by the switch, the voltage that is being blocked by the switch when it is in off state, is also decided by the external circuit elements. In this case, the switch is blocking a voltage of Vd. Let us try to take a look at the energy lost in the switch in one switching cycle Ts. What is the energy lost? Energy lost is the area under the power waveform. So that means the area A indicated here. So that is the energy lost in switch during one switching cycle. And that can be seen as a sum of two areas. In fact, it's an approximation which is valid because these times, the transition times and turn on turn off times, are usually very small. So the waveform Ps is approximated by the sum of two waveforms, Ps conduction and Ps switching, Ps underscore SW and Ps underscore COND. Now this integral of 0 to Ts Ps dt, which is the area, is now the sum of three areas, area A1, A2 and A3. So area A1 corresponds to the energy lost in the switch during conduction, during the on state, and the sum of areas 2 and area 3 indicates the energy lost during the switching transitions. For example, the area A2 gives us the energy lost in switch during the turn on transition, and the area A3 gives us the energy lost in the switch during turn off transition. The peak value of conduction loss is V on multiplied by the current I, and the peak value of switching loss is 1 by 4 Vd times I, as indicated in these two plots. The areas A1, A2 and A3 can be calculated by simple mathematics. A1 will be equal to V on I T on, and the sum of A2 plus A3 will be equal to 1 by 6 Vd I into TSW on plus TSW off. So the area A1 is referred to as ES conduction here, that is the energy lost during conduction, and the sum of the areas A2 and A3 is referred to as ES underscore SW, the energy lost during switching. Now if you want to calculate the total power loss in the switch in watts, which is the average power loss over one switching cycle Ts, we should multiply the energy by the switching cycles per second. So Ps is equal to Es multiplied by the switching cycles per second, which is nothing but the switching frequency. So Ps is equal to Es into Fs. So the conduction loss in switch is denoted by Ps conduction. It's again the average over one switching cycle. So when we say conduction loss, what we mean is the average conduction loss over one switching cycle is Es conduction multiplied by Fs, which is V on into I T on Fs, and the average switching loss, or simply switching loss in the switch in watts, is Ps underscore SW, which is the product of Es underscore SW multiplied by Fs, and that is given by this expression 1 by 6 Vd I into TSW on plus TSW off multiplied by Fs. So the conduction loss in a switch depends upon the on state voltage and the on state current I, and T on divided by Ts. T on multiplied by Fs is same as T on divided by Ts. This T on divided by Ts is the ratio of the on time to the total cycle time. So that is popularly known as the duty ratio. And the switching loss in the switch depends upon the blocking voltage Vd and the current in on state I, the device switching transition times TSW on and TSW off, and Fs. Fs is a switching frequency. Let us consider another typical example which is widely found in power electronic circuits. When the load is not a pure resistor but a combination of inductor and resistor, and when the inductance is fairly large, the RL load can be represented by a constant current sink. So that is what is represented here as I. Since this current I has to flow all the time, whenever the switch S is turned off, it is like open circuit for this current source. So we will need another switch S bar shown here to act as complementary to S. So whenever S is turned off, it makes sure, the S bar switch makes sure that the current has a path to flow. This I flows through S bar. Okay, so that is the difference here. Our interest again is to find the power lost in switch S. So we need to look at the product of voltage and current, voltage across the switch and current through the switch. So that we again find by using KVL and KCL. So if you apply KVL, Vs is equal to Vd plus Vs bar, and if you apply KCL at this node where S and S bar connect and the current source is also connected, at that node if you apply KCL, Is plus Is bar is equal to capital I. So when S is on and S bar is off, in that state the switch current Is is equal to capital I, and the switch voltage Vs is given by V on, which is also a function of Is typically, which is a function of the current flowing through the switch. And when switch S is off completely and S bar is on, Is is equal to 0, no current flows through the switch. And what is the voltage across the switch? The voltage across the switch is Vd plus Vs bar, and if Vs bar drop is neglected, because our interest is to look at the switch S, we are approximating this by capital Vd. This analysis can also be done by including that drop Vs bar. Now let us look at the waveforms of Vs and Is. So let us say initially the switch is off, so that means S bar was conducting, so the current was flowing through S bar. So Is bar is equal to I. Is bar is not shown here because our interest is the switch S. Now when we give a on signal, the turn on signal, turn on command to this switch S, the current through the switch starts rising. The current Is starts rising as shown by this red color waveform. However, since KCL has to be maintained, that means Is plus Is bar has to be equal to I, and that can only happen when Is becomes equal to I. Is is still rising, so it has to reach I. Only when Is reaches I, Is bar will become 0. So as long as Is is less than I, Is bar will also be conducting. So both switches will be conducting and contributing to this current capital I. Since Is bar is still non-zero, the voltage across the switch Vs in this current rise interval, the current rise interval continues to be Vd, which was earlier in the off state also. So the voltage fall interval does not start as soon as the current rise interval starts. In fact, the voltage fall interval starts after the current rise is over. Why? The voltage across the switch Vs has to be Vd as long as Is bar is finite, and Is bar will be finite as long as Is is rising and is not equal to I. So that is the difference between the earlier example and this example. In this example, the current rise and voltage fall intervals occur separately. In fact, the voltage fall interval follows the current rise interval. Similarly, in the on to off transition, voltage rise happens first and then the current fall. The switching transition times TSW on and TSW off now have two components in each. So TSW on is the sum of TRI plus TFV, so the current rise interval, duration of current rise interval TRI, and the duration of voltage fall interval TFV. Similarly, TSW off is the sum of TRV plus TFI, where TRV is the duration of voltage rise interval and TFI is the duration of current fall interval. Now let us look at the energy lost in switch during one switching cycle. It's again the area A shown here. Now the area A can be written as sum of three areas approximately. So A1 plus A2 plus A3, and the area A1 corresponds to the energy lost during conduction, and the areas A2 and A3 correspond to the energy lost during the turn on transition and turn off transition respectively. The approximation is valid for most practical purposes because the times are very small. A1 is equal to V on I T on, and A2 plus A3 is equal to half VD I into TSW on plus TSW off, as shown in these expressions. And the peak value of switching loss is now VD times I, as indicated in this plot, and the peak value of conduction loss is anyway V on times I. The power loss in watts, that is the average power loss over one switching cycle TS, can be again found by multiplying the energy lost in one cycle by number of switching cycles per second. So that is PS is equal to ES times FS. PS is again sum of two average losses, PS conduction and PS switching. So the average conduction loss in the switch is the energy lost in conduction in one cycle multiplied by the switching frequency Fs, which is V on into I T on into Fs, and the average switching loss in the switch in watts, which is PS underscore SW, is ES SW times Fs, which is half VD into I into TSW on plus TSW off times Fs. So to summarize, the power loss in switches has two components: conduction loss and switching loss. The conduction loss is a function of the current flowing through the switch when it is on, which in turn decides the voltage drop across the switch in the on state. Magnitude and direction of the current flowing through the switch is decided by the remaining circuit elements. The conduction loss also depends upon the ratio of the on time, that is the time for which the switch is on, and the time period of the switching cycle. This ratio is popularly known as the duty ratio of the switch. So the conduction loss in a switch is a function of the current flowing through the switch and the duty ratio of the switch. Let us take a look at the second component of loss, that is the switching loss. The switching loss is a function of the off state blocking voltage and the on state current, the turn on and turn off transition times, and the switching frequency. The off state blocking voltage and the on state current are decided by the remaining circuit elements. Typical values of the transition times, switching transition times, the turn on and turn off times are specified in the manufacturer's data sheet of the switch. However, the actual times of transition depend upon many parameters: on state current, off state voltage, elements of the control circuit of the switch known as gate drive circuit, and the internal temperature of the switch. The switching frequency Fs can be chosen by the user subject to the constraints posed by the type of switch, the power loss, and the size of the power converter. So this is how we can estimate the power loss that occurs in switches in a power electronic converter.